And we're going to see Jonah Gaster, who's going to tell us about the Markov ordering of the randomness.
Yes, thanks for the intro. Thanks very much to the organizers for the invitation to speak. It's a pleasure to be here. We've seen a dazzling array of beautiful talks about groups and their geometry this week and last week. And as you may have noticed from the title or the abstract, this talk will not be like that. There will be no deep, beautiful theorems about groups and their geometry. There also won't be any theorems about groups or deep theorems for that matter. But I do want to tell you a beautiful story that I find quite amazing. Yes. If you really look hard for one, sure. So, yeah. Okay, just wait. So yes, the story of the Markov numbers is amazing and dazzling because the Markov numbers affect many different areas and somehow they say something about many different things. For me, it's a story about hyperbolic geometry and SL2Z. So ultimately, we will come back to hyperbolic geometry, but I'm going to start going back in time a little bit and telling you some definitions of things, and they might sound like, who cares? There's some numbers, but I swear they're amazing. And so if you've seen this story before, then please indulge me, and I'm sorry. And if you haven't, then I hope to convince you that it's a beautiful story. So the first definition is who the Markov numbers are. So the Markov numbers are integers so that you can find another pair. Well, I'm just looking for triples that solve this simple cubic equation, x squared plus y squared plus z squared equals 3xyz. So, okay. Oh, I squared the last one. Thank you. Thank you. You've seen this before. Yeah. Okay. So, for example, 1, 2, and 5 are all Markov numbers because this triple satisfies this equation. So maybe a first question to ask about this equation is how do you list all the integral solutions? How do you find them all? And the observation that makes it possible to do this is, well, you notice that if x squared plus y squared plus z squared is equal to 3xyz, then there's another solution, which is to say it's a quadratic equation in x. So if I found one solution, then there's a pair of solutions that add up to 3yz. So there's another integral solution. So you should interpret that as a kind of graphical move. If I found a solution, xyz, then I can find another solution with yz. Maybe I call it x prime, 3yz minus x. And what that allows you to do is sort of fill out the labels on a tree. So I should think of this as a trivalent tree, and I'm labeling the complementary components of this trivalent tree. So, okay, for my own reasons, I really want to start with 1, 1, 2. And now when I do my flip move, I do 3 times 1 times 2 minus 1, I get 5. Here I'm going to get 13, 34. Here I'm going to get 29, and so on. And what I'm doing is filling out a system of labels. So you should think of this as a map. I'll call it lambda sub m. It's the Markov labeling of the set of horospheres. Sorry, Donnie, just going to do this. So I'm labeling these complementary regions. Why is it a tree and not a forest? Yeah, because the numbers go monotonically when I go. Say it again. If right. So okay. So here's an exercise. So yes, I accept the question. So so there's a labeling from this system of horospheres to the Markov numbers, and the exercise that you're going towards is the fact that this is onto. And it's onto because if I pick a triple, then I can choose the largest one and flip and decrease. And as I do that, I decrease, and I'm tracing my way back to say they're all equal to 1. So I'm at the root of the tree. What's much less obvious, in fact, a big open conjecture that's 100 years old, is that this is also 1-to-1. So you won't see this. So MUC is the Markov uniqueness conjecture. It's like the central problem in the story of the Markov numbers, which you're not supposed to think about it. It's not, it's one of the list of problems that people say don't think about it. It's too hard. There's nothing to do. There's a paper written in the 90s that features this problem and the Collat's conjecture and like, I don't know, the Riemann hypothesis or something. Don't think about these problems is the title of the paper. So, but anyway, okay, so that's too hard, but it's still a fascinating subject. Yeah, so I need to try to convince you that these numbers are beautiful. So before I go towards hyperbolic geometry, let me point out that one manifestation of their beauty, the reason that Markov cared about these numbers, the reason that this equation, well, this equation doesn't come from nowhere. So it turns out that the Markov numbers are some kind of record. So they record the extremal irrationals. They're a recording of which irrationals are most irrational. So here's how that goes. So there's a old theorem of Dirichlet. If you take an irrational number, then you can always find infinitely many rationals so that you're doing a very good job of approximating alpha with the rationals. So that's a silly thing to say. The rationals are dense. Of course you can. So it would be also silly to say, oh, I could always make this less than 1 over q. Well, of course you can. This is an irrational. I just picked the right numerator to get as close as I can. But Dirichlet's theorem is that you can do one order better than you thought you could, 1 over q squared. So every irrational can be unreasonably well approximated by rationals. And then Hurwitz came a little bit later and noticed actually you can replace the 1 over q squared with 1 over square root 5 q squared. And moreover, and this constant that you find is sharp because of the number. Well, you might be guessing it's the golden ratio. It's where the root 5 is coming from. Okay. So Markov observed that, well, if you throw out, so if you remove the golden ratio and actually all of its cousins, everything that looks like the golden ratio, which is to say anything in the same SL2Z orbit acting by Mobius transformations, if you remove all these numbers, then in the conclusion, you can replace 1 over square root 5 q squared with, well, in Hurwitz's theorem, you can replace 1 over square root 5 q squared with 1 over square root 8 q squared. And you can keep going. So now again, this is sharp because in this case, it's because of what's called the silver ratio. 1 plus root 2. And again, I remove the silver ratio and all its SL2Z orbit, and there's an improvement, a slightly better constant. And what you get is a discrete sequence of constants. So they're in the denominator, so I'll take the reciprocal. This sequence of constants increases strictly and approaches 3. And Markov's amazing theorem that I still just find unbelievable is that this sequence is just a record of the Markov numbers. So it's 9 minus 4 over 1 squared, that's the first Markov number. 9 minus 4 over 2 squared, that's the second. 9 minus 4 over 5 squared, that's the third, and so on. So somehow from the story of how do you do the best job you can, or what's the worst best job you can do of approximating reals by rationals, you find these beautiful, simple integral solutions to this nice equation. So that's what I find most incredible about the Markov numbers. But okay, so what to say about them? Well, by the way, I should say that a lot of the renewed attention in the Markov numbers in the past 10 years was spurred by a book written by Aigner, who wrote a beautiful book assembling a lot of the different points of view on the Markov numbers. So it's a great resource. And Aigner noticed the following idea. So, of course, you're geometric group theorists. You know trees like this. You love trees like this. You know another way to label these horoballs. So there's another labeling. And that's the fairy labeling, where I record the location of a horoball with a rational. And here I'm going to choose my rational to be between 0 and 1. So I start up here. This is going to be 1 over 0. Here's 0 over 1, 1 over 1. And now I do the fairy addition rule. Every horoball gets a coordinate, gets a location just given by a rational. And now I can define the Markov number in position P over Q. That's going to be the Markov number I see if I look at the horoball whose coordinate is P over Q. So M01 is 1 and M11 is 2 and so on. And that point of view, it transports so there's a natural ordering on the Markov numbers just by their size. And that you can use this indexing to find an ordering on the rationals. So the second part of this definition is I'm going to say P over Q is, let's say, Markov less than P prime over Q prime, if and only if the P over Q Markov number is less than the P prime over Q prime Markov number. So this is the Markov ordering of the rationals. And Aigner's question in his book, or among his various things, one of the things he asked about is, what is this order? And how can you predict it? Like, what's the Markov order between 19 over 1,000 and 17 over 900? How can you tell? Yes.
We're not supposed to think about the uniqueness conjecture that you're about to erase.
Yes.
Just, like, designed in an attempt to solve that conjecture, because
No, I think it was an attempt. Well, the uniqueness conjecture predicts that this is actually an order. Technically, it's only a partial order because there could be horoballs with the same label if we don't know the Markov uniqueness conjecture holds. I think this Aigner's focus on this ordering was an attempt to stop worrying so much about the uniqueness and see what else you can say about the Markov numbers. Right. In fact, Aigner conjectured 3 things that predict when P over Q is Markov less than P prime over Q prime. And those 3 things are there's a fixed numerator, there's a fixed denominator, and there's a fixed sum conjecture. So in the fixed numerator, of course, P and P prime are equal. So these are all precipitating P over Q is Markov less than P prime over Q prime. In the fixed denominator problem, the denominators are equal. And in the fixed sum problem, their sums are equal. And the data here is just saying, well, if the numerators stay the same and you increase the denominators, then the Markov ordering should go up. And if the denominators are the same and you increase the numerators, then the Markov ordering goes up. And if the sums are the same and you increase the denominators, then the Markov ordering should go up. So graphically, if you're thinking about the QP plane, you're sitting at a point Q comma P, and Aigner's conjecture is if you go up this way, the Markov number goes up. If you go that way, the Markov number goes up, and if you go that way, the Markov number goes up. So this was subsequently proved by some cluster algebra combinatorial people, Lee, Rabideau, and Schiffler. There's another version, some other names, so I won't list them. So there's others. Using cluster algebra techniques, using what are called snake graphs. So there's another perspective on the Markov numbers, which, okay, I'm just going to say something parenthetical, and I find it amazing, and I can't explain it, so I won't explain it. But it turns out that the Markov number for P over Q is a count of the number of perfect matchings in a graph that you obtain in a natural way from the straight line segment in the QP plane from 0, 0 to QP. So there's a way, okay. There's a way to turn this line segment, recording how it's going through the squares, turn that into a graph. That's called a snake graph. And then you can record what the Markov number in that position is by counting the perfect matchings in that graph. It's kind of an amazing point of view, and it led them to proofs of Aigner's conjectures. Okay, so then subsequently, a different proof that I find much more transparent and beautiful. So this was also proved later by McShane using hyperbolic geometry. So of course, that's the one that I want to focus on. And if you use McShane's point of view and push a little bit, then you can prove the following theorem. So there's a pair of constants, sigma minus and sigma plus, which are precise, but their precise value doesn't really matter. It's something like -1.2 something, -1.1 something. You could write them with logs and square roots, so that if L is a line in the QP plane of slope, of rational slope, then the following holds. First of all, if the slope is smaller than sigma minus, then the ordering is let's see, smaller than sigma minus is decreasing with Q along this line. And if the slope is bigger than sigma plus, then same story, but increasing. And third, if the slope is in between these two, well, let me say it this way. For slopes in between these two, there exists non-monotone examples. So there exist lines in the QP plane of that whatever slope you picked, where the Markov ordering is not monotone along that line. So this is a characterization of what happens along lines in the QP plane. Aigner cared about lines of slope 0, infinity, and -1. And this is saying, well, actually, you could compute what happens along lines more precisely if you follow the hyperbolic techniques of McShane. Any questions? Okay. Okay, so of course I have to say where hyperbolic geometry comes from. So far, it doesn't sound like hyperbolic geometry at all. So part 2 is why hyperbolic geometry? So this part has been known for a long time. It was discovered by Kohn in the 50s that the Markov numbers are related to hyperbolic structures on punctured tori. And so I mean complete finite volume hyperbolic structures on punctured tori. And here's one way of getting at that relationship. So here's a group. You wanted a group, here's a group. So you take an ideal quadrilateral in the hyperbolic plane that's as nice as it can be with vertices 0, -1, 1, and infinity. And I'm going to take a pair of side pairings. And, you know, this example is like maybe the first hyperbolic surface you should look at, because it's just so simple. Like you have to guess a Mobius transformation that takes this side to this side. I think if you're being reasonable, you're going to guess 2, 1, 1, 1. And for this side to this side, oh, I did that backwards, didn't I? 2, -1, -1, 1. Takes 0 to -1, takes 1 to infinity. This way I would do 2, 1, 1, 1. So here's my A and here's my B. and I let gamma be the group generated by these two transformations. And this group satisfies, well, of course, we can all see that the quotient is homeomorphic to a punctured torus. I find a finite volume hyperbolic structure on this punctured torus. And I just want to notice that the cusp holonomy, okay, if you pick the right representative, is going to be -1, -1, 0, 6. Okay, you could complain. Maybe you're thinking, well, why did I put the negatives there? Or maybe you already know the answer, in which case you're not complaining. But why do I have the negatives there? So technically speaking, these are isometries of H2. They're in PSL2Z, but I chose lifts already in SL2Z. So I'm just going to pretend it's in SL2Z. And if I compute the cusp holonomy for this lift into SL2Z, I'm going to find minuses there. Even though in PSL2Z it's the same as 1, 1, it's important that in SL2Z I find minuses. So you'll see why in a moment. Yeah, so that's my surface. And I should notice that this group is quite beautiful. This is the commutator subgroup of PSL2Z. Quite natural. So the fact is, oh yeah, right. I want to notice that the triple of curves A, B, and their product is also interesting. So in a couple of ways, first of all, these three curves are the three systoles that came up in the last lecture. The systole is the shortest curve on the surface, so you can check that these three curves here are the three shortest curves. And this trio is a trio of simple closed curves that pairwise intersect once on the quotient surface. Did I name that yet? Let's say that's X. So the fact is, the connection to Markov numbers comes here. So the fact is that, here, maybe this is 1 and 2. So trios of curves, as in this second point, when I take their traces in this representation, I find triples of integers. Oh, that's what X was for. Okay. Sorry. H2 mod gamma. Trios of curves pairwise intersecting once are in correspondence with triples of natural numbers that satisfy the equation x squared plus y squared plus z squared is x, y, z. No 3, not an accident. There's no 3 there. Yeah, why does this fact hold? Well, essentially it's because if I take a trio as in the second point here, then I look at the commutator of 2 of them, and I know it's going to be conjugate to the commutator of A and B, so I know the trace is going to be -2. That's where the negative's important. And if I let X be the, so if I have a triple, I let X, Y, and Z be their traces, and now I turn this equation following what's called the SL2 trace identity, which tells me that the trace of AB plus the trace of AB inverse for any matrices A and B in SL2, actually it doesn't matter what fields, is the trace of A times the trace of B. And if I just use this simplification procedure to boil down this trace of a commutator equals -2, you're going to find this equation. So it tells you that triples of curves that pairwise intersect once satisfy this Diophantine equation that looks like the Markov equation. And it's not too hard to see that solutions of the original Markov equation, integral solutions, are in one-to-one correspondence with integral solutions of this new equation. You just get from one to the other by dividing by 3. You just have to check you think about what's happening mod 3, and you find out that any integral solution of this one, they all have to be divisible by 3. So I can divide and get a solution to this one. Right. So the point, therefore, is that the Markov numbers are just 1/3 the trace spectrum of, that is to say, I look at simple closed geodesics on H2 mod gamma. And for each one, I can take its trace. I mean, if it bothers you lifting to SL2Z, you could take the absolute value of the trace, but I already chose representatives in SL2Z, so you don't need the absolute value now. I find the Markov numbers as traces of simple geodesics on this hyperbolic surface. So that's the geometry. That's why hyperbolic geometry is relevant. And actually, just because we're here, because the length of a curve is explicitly related to the trace of the curve by this increasing function, you can rephrase the Markov uniqueness conjecture as the statement that if alpha and beta are simple closed geodesics with equal length, which is to say equal trace, then there exists an isometry of the surface taking alpha to beta. So it is a statement about hyperbolic geometry of this hyperbolic surface. How can simple geodesics have the same length? Of course, if they differ by an isometry, they'll have the same length, but are there any other accidents? That's what the Markov problem is asking. I should point out that you could be less ambitious than the Markov uniqueness problem and just ask, well, is the number of simple closed geodesics on a hyperbolic surface bounded by the topology? Is there just any bound at all? And I have no idea. I don't think anybody does. But I should. Yeah, did I not say that? Number of simple closed geodesics. Yes, that's the whole point. Thank you. Yeah, of precisely equal length. That's the whole problem. Or, I mean, less ambitiously, what's the best bound you can give in terms of the length and the topology? A remark to make is if you remove simple, the answer is no. So it's definitely a question about simple geodesics on hyperbolic surfaces. This is something noticed by Horowitz. And then really this is a statement about representations into SL2 that Horowitz noticed, and then Randall noticed that tells you something about lengths of curves. So I think I'm ready to talk about McShane's proof of Aigner's conjectures. And right, so of course, something we all know, simple closed curves on a punctured torus on this H2 mod gamma, these are in correspondence with lines in the integral homology. So S is my surface, lines, rational lines. And McShane and Riven, in their counts of simple geodesics on punctured tori, they're used crucially the fact that the length function. So in every primitive integral homology class, there's a unique geodesic representative that's shortest, and it will be the simple curve in that primitive homology class. And I can record its length. So that gives me a function. And if you notice that this length function satisfies a triangle inequality, you can extend this length function. So this extends continuously to a length function on all of the real vector space. Right, and this extension has strictly convex unit ball. It extends continuously to it's a homogeneous function. So it extends to a homogeneous function, which is to say, if I measure the length of t times v, it's t times the length of v. So, right, so to connect this to the Markov problem, again, because of the simple relationship between length and trace, because length is a half cosh inverse of a half of the, 2 cosh inverse of a half of the trace, the Markov ordering between P and Q and P prime Q prime, I'll try that again. P over Q is less than the Markov ordering than P prime over Q prime, if and only if the length of QP is less than the length of Q prime P prime. The length and the trace are recording the same ordering. So McShane's observation is just this Markov problem is about the unit ball, the L unit ball. Remark, to make this literally true, you have to, this requires choosing the right identification of H1, well, let's say it this way, of the integral homology with Z squared. Because really, when I talked about the Markov problem, the Markov ordering, I was fixing where the labels were on the horoballs. There's some normalization that was already implicit. So I need to also have some normalization over on this side, and the normalization requires you to place the systoles at 1, 0, 0, 1, and minus 1, 1. So these are the systoles. Okay, and then this becomes literally true. And yeah, so now McShane can give her a very simple proof. And it goes like this. Choose a point, choose a primitive point. So here I am at some primitive point. And I look at the level set of L through this point. So it's some strictly convex curve. I look at where it intersects the x-axis. And oh, right. Forgot to notice this. Yeah, the surface has some beautiful symmetry, which we haven't exploited yet. So we should exploit it now. So L, this length will be invariant under the symmetries of the punctured torus we built, which in this case, I've got an order 3 symmetry and an orientation reversing order 2 symmetry. And now I can use it. So I take this place on the same level set intersecting the x-axis, and I know that I've got several other points of the same length as well, just by taking the orbit under this finite group. And I know that the unit ball, or sorry, that the ball with this level set contains this hexagon by convexity. And I picked Q over P here, and you can notice by convexity that it had to be on the left of this vertical line. Otherwise, it would violate convexity because there's a support plane for this ball through this point. Okay, so I draw the vertical line through this point, and I notice, again, just by convexity, it has to intersect this level set somewhere. And that tells me that as I move up along this line, the length has to be going up. I'm leaving the ball. So the ordering of the length goes up in this direction. And the same argument applies to horizontal lines. And then the small thinking you have to do for lines of slope -1 is to use the other symmetry and notice that, well, if I have Q over P, then I also have P over Q on the same level set. And again, by convexity, I already have two intersections of this line with my strictly convex curve. So I know if I go in this direction, it goes up. It's a very simple explanation of what Aigner was observing. So the program for proving the theorem I told you is to just push McShane's proof further. So to improve McShane's proof, you need to compute corner slopes. You need to know the extremal lines for this strictly convex body. And so when I pick a line of rational slope, I need to know the angles of the slopes there. So that's what you do next. Well, maybe before I do that, I just want to make a remark. So, right, a strictly convex planar curve of length L passes through big O of L to the 2/3 lattice points. So this is an old result of Jarnik from the early 20th century. In fact, Jarnik was more precise about the constant and kind of sharpness. And this tells you something in this context. It tells you that if you're looking for curves of the same length, you can find at most big O of L to the 2/3 of them. And if you translate that into a bound for the Markov labeling problem, the size, like how many horoballs can have label n, you learn from Jarnik's theorem that it's big O of log n to the 2/3. There's a translation between Markov numbers and lengths. It involves a log. So this is the best bound I know of, and I'd love to learn better bounds. Of course, Markov uniqueness says it's 1, but that's the best we can do. Okay, that's kind of a lie. I mean, this is the best uniform bound I know. You can give much more precise bounds. For instance, I think the best one I know is you can bound this differently by 1/2 the number of roots of -1 modulo n, which is one way of proving the Markov uniqueness holds when n is a prime power, because then there's exactly 2 roots of -1, so I'm going to get a 1 here. That's Markov uniqueness for prime powers. You can give a hyperbolic geometry proof of this, by the way. It sounds like a number theory fact, but you can make it a hyperbolic geometry fact. In the worst case scenario, your Markov number is a product of primes, all of them congruent to 1 mod 4, so that they give you roots of -1, and you find out that this bound here looks like 2 to the k. So if you compare this size as a function of k to this, in the worst case scenario, it's much worse. The hyperbolic geometry bound sees more than you can see from this number theory perspective, at least uniformly. Okay, so yeah, I mean, that kind of challenges. Can you do any better than this? So how do you compute corners of the norm ball? How do you compute slopes? Yes.
This is a hyperbolic geometry fact. Like that statement.
Yeah. Well, you can prove this from the point of view of the hyperbolic geometry of the punctured torus as well, even though it sounds like a arithmetic thing. Yeah. So maybe there's not really a difference between an arithmetic fact and a hyperbolic fact, but anyway, I know I just claimed there was, but yeah. Okay, so how do you compute corners of the norm ball? Well, there's a rephrasing of this that I think is more convenient. So there's a function that was introduced by Vladimir Fock, which is related to all of this. So in fact, the geometry of this ball is in some sense dictated by the following function, Fox function. So it's a function from Q intersect 0, 1 to the reals, where I take P over Q and I return the hyperbolic length of the QP curve, but I weight it by Q. So it's I find it quite pleasant. It's like some ratio of the hyperbolic length to an arithmetic length. And they balance each other out beautifully. And this function is continuous, convex, and decreasing, strictly convex. And you can see all of those things from the point of view of the unit norm ball, because the Fock function is really just saying you're looking along lines of slope, of a rational slope, and you're asking, when I project the QP primitive point to the vertical line with coordinate 1 in the first coordinate, how much do I have to shrink? The Fock function is exactly how much you have to shrink to project to this line. So it's somehow dictating exactly there's a transformation that goes between the boundary of this ball and the Fock function. So learning about the boundary slopes for the unit ball here is the same as learning about the derivatives for a Fox function, the one-sided derivatives for the Fock function. And that's the thing that you can compute. So how do you do that? So what are you trying to do? Well, you're trying to estimate one-sided limits. So I need to do P over Q plus epsilon minus P over Q over epsilon, and I need to take the limit from either side. So how do I approach P over Q from either side? Well, I should choose R and S that intersect P over Q once. So plus or minus 1 if I want to be on the right or the left side, and then I twist. So I can do this one-sided limit by taking a sequence of points approaching P over Q, and I build them by twisting. So I'm going to do NP plus R over NQ plus S. Now I divide by the difference. If you do this, you'll get Q times NQ plus S. And when I write this limit out, I'm going to find, well, so the Fock function is the length divided by the denominator. I'm going to get some cancellation. I'm going to find Q times the length of this twisted curve minus NQ plus S times the length of the QP curve. And this project then is, to finish this computation, you need to estimate the length of the twisted curve. And of course, you're thinking, oh, I know that. It's n times the length of the QP curve. I think I switched these. Anyway, that's n times the length of the QP curve plus the length of the RS curve. And you're right, that's true, but that's only true up to an order that goes to 0 against n. But that's not going to work here because n is going to infinity. So I really need tighter control on this hyperbolic length than you get from guessing. And here you get to use a miracle, which is on any hyperbolic punctured torus, on a hyperbolic punctured torus, simple geodesics pass through 2 Weierstrass points. And that's telling you something much more than you know in general. So Weierstrass points are the fixed points for the elliptic involution. And it means that when I have a Markov triple, alpha, beta, gamma, on the surface, I must see, so a triple of curves pairwise intersecting once, I must see a complementary triangle. And the vertices are Weierstrass points. And so I can pretty explicitly estimate, actually not just estimate, but compute this length of the twisted curve by building its geodesic representative. So this is the twisted curve. I twist gamma about alpha n times. And now this angle is this angle. So I can use hyperbolic trigonometry to express the length of this curve explicitly in n and the lengths of these three curves.
Like fixed points of the hyperelliptic, not counting a function.
Yeah, that's right.
So what do them?
Yeah. Yeah, so then the proposition becomes, you can compute this. The hyperbolic length of the twisted curve is going to be something explicit. Okay, the leading order term is what you think. It's n times the length of alpha, but there's a constant term that's some kind of delicate balance of all these lengths and the angle. Well, the angle is a function of the lengths as well, plus big O of something that goes to 0 very quickly. Yeah, so then you take this explicit estimate and you plug it in here, and then you win. And so you computed the corner slopes, and that's how you do the generalization of McShane's proof. Any questions?
Say weekly, why the miracle occurs? I guess it wouldn't be a miracle.
Oh, no, it's actually it's not a very complicated fact. So let's see if I can say it. So it's just because the elliptic involution is acting by minus the identity in homology. So it's when I have a simple geodesic, I know that it's the same set of points for the negative homology class. So that means that my map must be taking the circle to itself. So there's two fixed points. So those are the Weierstrass points. Yeah, so that's it for the proof of that theorem. So I thought I would just finish with a little discussion of, well, my last section is, why is this problem hard? Why is the Markov uniqueness problem hard? Okay, so the first thing I want to say is, if maybe a naive guess for how you should do this is like, oh, well, people nowadays know how to count the number of simple geodesics on a hyperbolic surface really well after Mirzakhani. And before Mirzakhani, McShane, and Riven, they knew how to count simple geodesics on this hyperbolic surface. In fact, McShane and Riven, it's pretty transparent from the point of view of this length function. The number of simple geodesics, simple closed geodesics on a hyperbolic punctured torus, well, it's going to be, so I have a unit ball in the QP plane for the L unit ball, and I'm scaling it up if I want to count simple geodesics of length at most L. So I'm just counting lattice points inside of this scaled version of the ball, and that's just going to be the area of the ball times L squared. So this is some constant that depends on the geometry of X, the area of that ball. And actually, McShane and Riven do even more. They bound the error term like L log L. So I just point that out to say, well, if you're going to try to count all simple geodesics, it's going to give you no hope to counting the geodesics of length precisely L, because the error term is nowhere close to what you'd want it to be. And actually, they say even more. There exists hyperbolic punctured tori X, where the error term in this count is genuinely, you can't beat L. So this is not a good way of trying to prove Markov uniqueness or really say anything about it. And I have one other reason why this is hard. So maybe if you were starting over and asking how you would do this naively, maybe your first guess would be, yeah, so I take, suppose alpha and beta are two simple geodesics of the same length. Why in the world should there be an isometry taking one to the other? Well, I do the only thing that you could possibly do. I cut open and I find, excuse me, I find a pair of hyperbolic pairs of pants with all the same boundary lengths and a pair of cusps. But we know hyperbolic pairs of pants, they're determined by their boundary lengths. There's an isometry from this to this. So I'm done. I solved the Markov uniqueness. No, of course I didn't. The whole problem is I need to glue it together to an isometry of the original surface. And to do that, I need to worry about the twist numbers. So for every simple geodesic, I can record a twist number as follows. So let's say the geodesic is oriented. So then I record the point that sees the cusp orthogonally, but I record it on both sides. And on the other side, when I glue together, there's going to be some distance that I move to get from this point to the other point. That's the twist number. So the whole problem of the Markov uniqueness problem is like, well, what can you say about the twist numbers? Apparently, Markov uniqueness conjecture tells us that the twist number is determined by the length. If it's true, the twist number is determined by the length. So how is it determined by the length? Or maybe less ambitiously, what twist numbers are possible if the length is L? Or maybe even much less ambitiously, suppose I throw out the modular torus and I ask, how many twist numbers could there be that land me back at the same point in moduli space? And I don't know. I think that's a really interesting question. I do want to mention one last theorem that says something about how bad the twist numbers are. So this is kind of bad news, or I don't know, or not. So the twist function, or maybe you should really think of the relative twist function. So I'm going to go from Q to the reals, where for P over Q, I'm going to record this distance over there, the amount of twisting, and I'm going to scale by the length of the curve. This function has graph in 0, 1 times 0, 1, which is dense. So it's like it just looks like gobbledygook. You can't tell. It's going to be very hard to read the twist numbers from the homology class. And that's another reason why this is hard. So I'll stop there.
You know, first there you have these directions from the ordering. Does it keep changing or is it increasing in the
Oh, you mean in the slopes? Yeah, so the slopes were like, there was a sigma minus and a sigma plus, and I know that it's monotone, decreasing with Q here or increasing here, or one of the two if I'm getting that wrong. And I know that in here, there are non-monotone lines. So are you asking me like, yeah. Yeah, so I have to admit that like I might just be too much of a noob with number theory. But like the problem is that the reason I only said there exist non-monotone examples is because you need to get lucky and find lots of primitive points on the line in order to be able to say it's not monotone. And you could be getting unlucky and there could be very few primitive points, in which case you can't really check monotonicity there. So you need lots of primitive points. So you need to like take a line far enough out that you find lots of primitive points and you can check non-monotonicity. So I don't know how to say the statement you're saying, which is for every line past the point, it'll be not monotone. I mean, I suspect it's true, but it's like something about primitive points on lines.